In this video, I'll talk about what a knowledge graph is and how it relates to large language models. This concept gained popularity around 2014 or 2015, then went through a period of stability, only to resurface in 2023 with the rise of large language models. The primary reason behind this resurgence is the issue of hallucinations in large language models. Hallucination is currently the biggest obstacle, preventing large language models from being practically implemented. It refers to the generation of unrealistic or fabricated statements, also known as false facts. So, how can we address hallucinations? There are two approaches. Improving the capabilities of large language models. In the future, we might develop new training methods that significantly reduce the hallucination rate of large models. However, current models still fall short of this standard. Confining the boundaries deliberately. This means restricting the model to a predefined boundary, within which it uses its understanding ability to provide responses. Within this boundary, we supply a large amount of factual information. Here, the focus is more on testing the model's understanding capability. This is not hard to understand. For example, if we give a person 100 articles to organize and summarize, it would be very slow. But if we give them to a large model with sufficient understanding ability, it can complete the task very quickly, which is a significant advantage. The next question is, where do these facts come from? Websites, for example. If we want to build an AI retrieval system, much of the information can come from authoritative websites. We also need ways to ensure the quality of this information. Company documents. These are often written by internal employees, whose quality we can generally trust. Databases. These store business-related data, often in systems like Oracle, ensuring a certain level of authenticity. Knowledge graphs. Another source of facts can be structured knowledge that combines company information into a graph format. Knowledge graphs can be understood as a way to store information, which we call facts, compared to other methods. The key difference of a knowledge graph is that it uses an entity relationship approach to store information. Entities refer to real-world objects such as people, locations, or companies. Relationships are the connections between these entities. For example, Lucas and Eric are person entities. There are two company entities. The arrows represent relationships, such as one person working at a company, another having worked there previously, or one company investing in another. This kind of structured data is what we call a knowledge graph. Simply put, it includes various entities and multiple types of relationships. Terms like leader or work are examples of relationship types. A knowledge graph differs from simple graphs by incorporating multiple types of entities and relationships. We can create domain-specific graphs, such as medical, financial, legal, or risk control graphs. Regardless of the domain, the core is always the definition of entities and their relationships, which represent facts. Now let's explore the advantages of this storage method compared to others. Intuitive representation, particularly for relationships. For instance, if we want to understand Lucas, we can locate Lucas's node in the graph and see his connections to companies, people, and other objects, as well as the relationships among those objects. Key information extraction. From two perspectives. From a document's content. The critical information in a document often lies in the relationships between key entities such as people, places, and elements. Extracting these relationships captures the core ideas of the document. In an RAG system, when documents are converted into vectors, these vectors attempt to represent the meaning of the text. However, it's possible that the summary in the vector omits critical entities or relationships from the original text. Combining knowledge graphs with vectors can bridge this gap. reducing the hallucination potential of large models. This is why knowledge graphs and vector databases often complement each other. For example, Microsoft's recent Graph RAG aims to balance the strengths and weaknesses of knowledge graphs and vector databases. However, there are challenges. Graph construction, ensuring the constructed information is accurate. Integration, effectively combining knowledge graphs and vector databases to leverage their advantages and reduce hallucinations. Understanding structured data. Unlike documents, knowledge graphs are inherently structured, containing critical information in their relationships. Teaching large models to understand and utilize this structure remains a significant challenge in the field.